let's take a look at an alternating series which converges and ask if we formed the 10th partial sum. In other words, we rolled out the first 10 terms in this series and added them up. The value that we get, what's the biggest we could be off from the actual true value of the entire convergent series. For alternating series, this is actually pretty easy to decide, because since it's an alternating series and it's converging, that means that each term is a little bit less than the one that came before it, and their signs are bouncing back and forth, positive to negative. So if we stop after 10 terms, the 11th term might say add on a little bit more, but then the 12th term would subtract a little bit that's less than what it was before. So basically you're bouncing around the final result by adding and subtracting and adding and subtracting. And so the error at the 10th partial sum is simply the magnitude of the 11th term. With this recipe, the magnitude of the 11th term would look like this. First of all, I don't need to worry about the -1 business because I'm doing absolute values, so I'm not even going to write it in there. And I guess I should use the wiggly approximate sign, not equals. This turns out to be about 0.0083-ish, rounded. And so again, this is a convergent series. It has a value. If we were able to add up an infinite number of numbers, the value that this would produce is what it is. We still don't know what that value is, but what we do know is that if we only added up the first 10 terms, we are only this much away, at most, from the actual true value of the series. And that's not bad after 10 terms. But let's say we were being really picky, and we wanted to go farther out into the series to make sure that the total that we were getting through any partial sum that we stopped at was no more than 0.00001 away from the actual final value. Again, not even knowing what this final value is, just how far away from it could we possibly be? Well, using the same idea is up here. Remember that if we stop after a certain number of terms, say after 20 terms, the amount that we're off at most is just the size of the 21st term, because we're dealing with an alternating series that converges. And so this means we just need the size of the n plus first term to be less than our target, to make sure that if we stop after n terms, the largest possible error we have left is this much. And since we know the formula for this series, and since we're working with absolute values, again, this thing here is either -1 or 1, and so inside absolute values it's irrelevant. And so using the formula for the series terms, I just set up this inequality and solve it. Now, solving inequalities can be anywhere from easy to excruciatingly difficult. This one leans towards kind of easy because we're solving for n, but it's in the denominator, but maybe we can just take reciprocals. So I'm going to take a reciprocal of the left-hand side. I'm going to take a reciprocal of the right-hand side. And what we have to remember is that if we're dealing with an inequality and you do that reciprocal business, you have to flip the direction of the inequality. And let's also remember that 1 over 0.00001 is the same thing as 100,000. So we need n plus 1 squared to be greater than 100,000, which means we need n plus 1 to be greater than the square root of 100,000. Which means we need n to be greater than the square root of 100,000 minus 1. And this number is, I'll just write it as 315 plus change. So it's like 315 point something, and that includes the minus 1, by the way. So this number is 315 point something. We're trying to count how many terms in the series we need to get to make our error no more than this tiny value. Since we're being told the number of terms in the series has to be bigger than 315 point something, that means we need to take 316 terms, right? Because 315.5 terms doesn't make sense. If we need more than 315, the next option is 316. And so the answer to the question is we need 316 terms or more in our partial sum, so that when we're done adding up that partial sum, we are no more than 0.00001 away from the true value of the series.